So let us apply Amperes law to determine the field due to a toroidal solenoid or a toroid. The Amperes law is the line integral around a closed path if B dot dl is equal to mu naught times I naught. Now this I naught is the current enclosed by the Amperian loop, and here the symmetry of the situation suggests that our Amperian loop should be in form of circular ring. This dotted line inside the solenoid is our Amperian loop, and the magnetic field is also in form of the circular rings inside the solenoid. So at any point P, the length segments dl of our Amperian loop and B will be parallel or will be in the same direction, and it will be along the tangent to the circle at that particular point. So B dot dl will be equal to B dl cos of 0 let me explain it once again. My pointer was off, so I will explain it once again. We are considering the Amperian loop in form of this dotted circle. This is our Amperian loop, and the magnetic field B in this case is also in form of circular rings. So if we divide our Amperian loop into small length segments, each length segment having the length dl, and we are considering just one of these length elements such as this small red line. This is our length segment dl. At this point B is along the tangent to the circle, dl is also along the tangent to the circle, both are parallel. So this side of our line integral will be equal to B dot dl cos of 0. There will be no dot here actually if if we are evaluating the dot product, then after evaluation the dot is left out. So our equation will be B dl cos of 0. Why we are taking the angle 0? Because at any point along this Amperian loop, B is along the tangent to the circle at any point, and dl will also be along the tangent to the circle at that particular point. So both B and dl will be parallel and the angle between them will be 0. So we will write B dl cos of 0. On the other side we are having mu naught times I naught, where I naught is the current enclosed by this Amperian loop. So if there are n number of turns per unit length, n is the number of turns per unit length, and the length of our Amperian loop is how much? It is 2 pi times r. R is the radius of this particular Amperian loop, not of the toroid but of the Amperian loop. So the total length of our Amperian loop is 2 pi times this r, and the number of turns per unit length is small n, so the number of turns in this much length will be 2 pi r times n, and I is the current carried by the solenoid. So the current enclosed by this Amperian loop will be equal to the number of turns contained in this much length, which is n times 2 pi r, and the total current carried by the solenoid, so by the toroid, sorry. So the current enclosed by this Amperian loop is n times 2 pi r times I. You must note that we have not written mu naught times I, but we have written mu naught times n into 2 pi r times I. because this much is the current enclosed by the Amperian loop. So while on the other side we are having B into dl. Now what is this closed integral dl? If you add up all these dl's around the closed path, you will get the circumference of this loop. So here this integral will give us 2 pi times r. So we will get here we will write this integral will be equal to b times b times 2 into pi into r, where r is the radius of this Amperian loop. So we will write b into the integral is equal to 2 pi times r, and this will be equal to this thing, mu naught times n into 2 pi r into I. So these two 2 pi r's will get cancelled, and we will be left with b on this side and mu naught times ni on the other side. Now here you can see 2 points. One is the point O and the other is point Q. This point is enclosed, this point is in the region enclosed by this toroid, and this point is outside the toroid. So the field on both the points will be equal to 0. It means that the magnetic field exists only in this tubular region inside the solenoid, which is the region bounded by the coil or by the tubular area of the solenoid. So the field lines will only be inside, there will be no field lines outside this tubular region, and just as the magnetic field existed only inside the solenoid and there was no field outside the solenoid. So the toroid is also the solenoid but twisted in form of a circle, and so just these field lines will also twist in form of circles but will remain inside this tubular region. Here you can see the toroid carrying current. This is the out direction for the current and this is the in direction for the current, and this out and in direction is shown by dots and circles over here. This is the out, this is the in. So in each turn the current will come out of the page over here and will go into the page over here, out of the page into the page, out of the page into the page. So here you can see the lines, three regions, B1, B2 and B3. This is the region which is enclosed by the tubular region but not enclosed by the currents. This is the region inside the tubular region, and this is the region also outside the region, outside this tube on which the current carrying wires are wound. So you are required to find the fields at these three regions. So calculate the values of the magnetic fields B1, B2 and B3 in these three regions. This would be your homework. just do it and send it to me on my personal WhatsApp.